Okay, we're going to finish up this section on applications of the integral by a quick review of vectors and then using calculus on our vectors. I'm going to go through this review fairly quickly. About the only difference I think you're going to see is maybe some notation, but you've worked with vectors long enough in physics. I don't think it's going to be an issue for you. So remember, a vector is in standard position if the initial point is at the origin. The initial point is where it starts. The terminal point is where the arrow is, where it keeps going. It has two components. It has a horizontal component and it has a vertical component. We can give those horizontal and vertical components, those two components, either in parentheses. So parentheses, we might see something that looked like 2, 3. That could either be a point in the plane or it could be a vector. If the terminal point to the vector is at the point 2, 3 in the plane, this could also be a vector. So you're going to have to read words, to pick up context from the problem. There's also the component form of a vector. If you saw 2, 3, but it was in component form, there would be no doubt in your mind it's talking about a vector. And again, it's talking about the horizontal component of the vector and the vertical component of the vector. This is going to look a lot like and follow really closely from our work with parametrics. Follows closely parametrics, all right? Because basically that's what's going on here, but it's vectors. All right, the magnitude or length of a vector, usually this is absolute value for us, but when there are two sets of lines like this with some bold letter in the middle of it, either a V or a W or a U or whatever, that means the magnitude or the length of the vector. And from geometry, it is the horizontal distance squared plus the vertical distance squared, and it's the square root of that. So it's just a straight line length in the plane, starting at a value and stopping at a value. If the magnitude of the vector is 1, then that vector is a unit vector. There are hats, I know. On your unit vectors, you might have, some number I hat plus or minus another number j hat. In physics, there are no hats for us in calculus. You can look in calculus textbooks. You won't see any hats on your i's and your j's. It doesn't make mathematicians right and physicists wrong, or vice versa. It's just how it is. If the horizontal component and the vertical component at the same time of a vector are 0, it's called the zero vector. It has no magnitude and it has no direction. Vector operations, you ought to be very familiar with these. Let's say we have two vectors, vector u and vector v. The horizontal component of vector u we're going to call u sub 1. The vertical component we're going to call u sub 2. Accordingly, horizontal component of vector v, v sub 1, vertical component v sub 2. Let's say k is some scalar or some real number value. We can add two vectors by adding their corresponding horizontal components and their corresponding vertical components. This gives us a whole new vector. We might call this vector w. We can subtract vectors. Where vector addition is commutative, vector subtraction is not, so be careful. Vector u minus vector v is not going to be equal to vector v minus vector u. So you have to subtract them in the same direction as what you're given here in your direction. So u minus v is the horizontal component of u minus the horizontal component of v. And it's the vertical component of u minus the vertical component of v. And that resultant vector, again, is going to be a completely new vector. We'll call it vector w. We can have scalar multiplication. If k is larger than 1, then this scalar multiplication will lengthen our vector. It will make it longer. If k is in between 0 and 1, it's going to shorten our vector. So this K will affect the magnitude of our vector. K can also affect, if K equals -1, which is the negative or the opposite, if K was equal to -1, it could not only affect our magnitude, it could affect our direction. This is the opposite direction. So if I have vector u and multiply it by the scalar -1, it will result in a vector that has the same magnitude but goes in the opposite direction. If K is any value, let's say it was -3, then K would not only affect the direction, it would also affect the magnitude of the original vector that it was multiplied by. All of things that we know. So this is why our vector work is going to follow our parametric work very closely, because we have a horizontal component, which usually can be given as some function in t, and a vertical component, which can be given as another function in t, and that combination will give us a vector. So our vectors could also look something like this, and that's why it follows very closely. Our vector work follows very closely what we did in parametrics. So most rules for calculus of vectors are the same that we have used for parametrics. These two are a little bit different. Make sure these go in your notes. Speed is the magnitude of velocity. So it would be, if this was the velocity vector, let's say we have the velocity vector v of t, which has horizontal component f of t and vertical component g of t, then we would say that the speed would be the magnitude of the velocity vector. So that would be f of t squared plus g of t quantity squared, and we would take the square root of that. The direction is the velocity vector divided by the speed. So again, you need to make sure that those two things are in your notes. All right, let's work an example. Find the velocity and acceleration vectors. So r of t here is the position vector, and r of t for us is notation that is used often on the AP exam. So we would have r of t be the position vector, v of t would be the velocity vector, a of t would be the acceleration vector. All right, and so if r of t is given to us as 3 cosine t, there's the horizontal component, comma, 3 sine t, there's the vertical component. Then following from our parametric work, since I said it follows it very closely, the velocity is just going to be the derivative of each one of those components. So here's -3 sine of t is now the horizontal component of the velocity vector, and 3 times the cosine of t is the vertical component of the velocity vector. Our acceleration vector is going to look like -3 cosine of t. That's the horizontal component. The vertical component would be -3 sine of t. So again, everything follows our parametric work very closely. Find the velocity, acceleration, speed, and direction of motion at t equal pi over 4. So I'm looking for velocity of pi over 4, which we said this was our velocity function. So that velocity would be -3 sine of pi over 4, comma, +3 cosine of pi over 4. And so that velocity vector would be -3 times √2 over 2, comma, 3 times √2 over 2. So there is our velocity vector at t equal pi over 4. Our acceleration vector at pi over 4, here's our acceleration vector we found in the last slide, would be -3 cosine of pi over 4. That's a 3, and I believe that's supposed to be -3. -3 sine of pi over 4. So this would be -3 times √2 over 2, comma, -3 times √2 over 2. Now remember, our speed is taking the velocity vector horizontal component, which we said was negative 3 root 2 over 2, and squaring it, plus the vertical component. That would be our speed. Our direction is going to be the velocity vector. And here, that velocity vector is negative 3 root 2 over 2I plus 3 root 2 over 2j. That's what our vectors look like. And then again, whatever we found that speed to be. 3 root 2 over 2 squared plus positive 3 root 2 over 2 squared. So fairly easy to do fairly quickly. So given a new position vector, here's a new position vector, write the equation of the tangent line where t equals negative 1. So equation of the tangent line, we need a point, right? An xy point, and we need a slope, dy dx. Just like parametrics, this is dy dt over dx dt. See how closely it follows our parametric work? So here's our y, here's the vertical component, here's the horizontal component. So if I want the derivative of this with respect to t, that's 3t squared minus 12. The derivative of this with respect to t is 6t squared minus 6t. I didn't do that too quickly. So there's our slope. We want that at t equal negative 1. So that's going to give us 3 times negative 1 squared minus 12 over 6 times negative 1 squared minus 6 times negative 1. So 3 times 1, that is negative 9 over, that's 6 plus 6, which is 12. 3 will go into both of those, so 3/4. And now we need, when t equals negative 1, we need to find our x-coordinate and our y-coordinate to get our point. Because we're still going to have y minus y1 equals the slope, which we said was negative 3/4 times x minus x1. So we need x1 and y1 right here. So at negative 1, 2 times negative 1 is negative 2 minus 3 times negative 1 squared, so that's just minus 3. And this is negative 1 plus 12. So this is negative 5. Our x-coordinate is negative 5, so minus negative 5, and then our y-coordinate is positive 11. So there's the equation of our tangent line. Find the coordinates of each point on the path where the horizontal component of velocity is 0. Well, we've got to find the velocity vector. That is 6t squared minus 6t. We need to know where that equals 0. So I'm going to factor that. That's true at t equals 0 and t equal 1. And we need the coordinates of each point on the path. So we're going to have 2 points. We need r of 0 and we need r of 1. So r of 0 is 0, 0. There's the coordinates of that. And r of 1 is 2 minus 3, so that's negative 1. And 1 minus 12, that's negative 11. So find the coordinates of each point on the path where the horizontal component of velocity is 0. The words matter, so make sure you read things carefully. I know I swung through that fairly quickly, but I think you're so comfortable with vectors and we worked so long on parametrics, I don't think that this is an issue for you. So come to class next time, we'll work some vector problems and then we'll get ready for our exam.